Je- J'ai rencontré Jean-François Joanny pour la première fois quand j'étais encore étudiant en licence dans un cours sur les polymères, donc où on nous avait parlé un peu pas mal de physique statistique. Et puis bon, on a eu un peu la surprise d'apprendre qu'il y avait beaucoup de physique riche même sur des choses qu'on appelait des blobs. Et que bon, ils pouvaient se coaguler de différentes manières et qu'il y avait des diagrammes de phase assez compliqués. Donc après, j'ai continué avec un stage de master à l'ESPCI où Jean-François était à ce moment-là directeur. Donc là, on ne le voyait pas, mais on entendait beaucoup parler dans les couloirs avec tout ce qui se passait à l'école. Donc maintenant, Jean-François Joanny est au Collège de France. Et donc, il y a plein de recherches passionnantes sur les propriétés fluidiques de la matière active, de la matière vivante, dont il va nous parler aujourd'hui.
Merci. Merci pour l'introduction. I'm supposed to speak English, so I will do the seminar in English. First of all, so I thank the organizers. It's been a very long time since I haven't come to Orsay to give a seminar, and I'm very happy to be here. What I want to do is tell you about some works that we've been doing over the last, I don't know, 5, maybe 10 years for some of the things. And what I want to try to do is exactly what Alexei said, is that there is interesting physics per se to do with tissues and assemblies of cells. So that's kind of the aim of the talk. What I want to talk about is how cells move in tissues. So I have this very general title. The first thing I want to show you is the real tissues, so the tissues that we study. There are essentially of two types. This type here is what people call multicellular spheroids. They are aggregates of cells, and they are used by, these are made of cancer cells, and they are used to test drugs. They are considered as one of the best ways to test drugs against cancer. The only thing that I want to point out is that they're almost perfect sphere, and that what this suggests is that they have an isotropic surface tension. And what I will try to convince you is that they are kind of droplets of cells with any property of the droplets you want to imagine. They are liquid, they flow, and things like this. They're also active. So for me, this is an active liquid. The other types of cells is what are called epithelial tissues. These are monolayers of cells. There's one here. So these are just cells deposited on a glass plate. They grow, they become confluent, and here they progress. So you see it from the side here and from the top here. And here is an example on which we work a lot, which is this is the internal part of your intestine, I mean, of one intestine, human intestine. And there is a layer of cell at the surface of these areas of what are called villi, and this is also a monolayer of cells of the type that I will talk about. The intestine is interesting for two reasons. There are lots and lots of data on the intestine. Also, this is the organ of your body that renews fastest. In 5 days, you renew completely all the cells of your intestine. They die, and they are born again in 5 days. So these are the kind of things I want to talk about. And in fact, I have two different subjects. As I said, I want to convince you that a tissue can be considered as a visco-elastic active fluid. And in the second part, I'll start from more applied things. When someone has a tumor, when it becomes dangerous, it's because cells migrate out of the tumor, and it has to migrate through tissues which are called extracellular matrix or conjunctive tissues. And what I want to discuss is how do cells migrate in such an environment? So these are the two parts. Let me start by showing you why a tissue is a fluid. Here's an experiment that I like very much. So these are two spheroids like the one I showed you before. And the experiments just consist in pushing the spheroids toward one another. They fuse, and they take this kind of peanut shape. Now, if you're like Liliane or me and worked on wetting, this is exactly what you expect if you take 2 drops of oil in water and you push them against one another. They make this shape, and then because of the surface tension, the whole thing becomes a sphere again, which just has twice the volume of the initial sphere. All people in the early 19th century, Plato and people like this, just studied this process And the law is that the square of the size of the neck here grows linearly with time. This is the initial radius. And then there is this ratio gamma over eta, which is a velocity just by dimensional analysis. It's called the capillary velocity. And you see that this law is almost perfectly satisfied. Even the scaling is good. So that pushes me in the same direction, that a tissue has an isotropic surface tension, but it also has a viscosity. Now, if I put numbers that you could extract from here, the surface tension is of the order of what you know for simple liquids, 1 millinewton per meter. Water is a bit high, but oil is like 20 millinewtons per meter. It's a little bit lower, but not very much. So viscosity is extremely high. It's like 10 to the 5 or 10 to the 6 or 10 to the 7 Pascal seconds. Water is 10 to the minus 3. So this is 8, 9 orders of magnitude more viscous than water, which means all the time scales are completely huge compared to what you would have for simple fluids. In particular, this kind of experiment that lasts for days. If you do it with 2 droplets of oil, it's instantaneous, and you have to be very clever to do it like this. So that's my second experiment. I point out to the same thing, that the tissue is, these spheroids are kind of droplets of cells. However, they're not entirely classical liquids. They're not entirely classical liquids because in a tissue, cells divide and cells die. So the total number of cells is not exactly constant. When a cell divides, you create an extra cell. And when a cell dies, a cell disappears from the tissue. So from a mathematical point of view, it's extremely simple to write. You write a conservation law. For a simple liquid, if you take out the flux, it gives 0. If cells divide, there is a division rate, and there is a death rate. Now, there are several ways for cell to die. The one which occurs in these spheroids is called apoptosis, which is programmed cell death. This looks very simple, but it's a little bit complicated because this division rate or the death rate depends on many, many parameters. They depend on the nutrients that the cell have, depends on whether they have access to oxygen, it depends to growth factors, which are things that you find in the nutrients and things like this. But it also depends on the mechanical state of the tissue. So there are 2 ways to write that. Either you say it depends on the density, or you say it depends on the pressure exerted by the cell against one another. If you're optimistic, there's an equation of state of the tissue. So the equation of state is how the pressure varies with density. And then it's kind of the same thing to say that it depends on pressure or it depends on density. It's not entirely obvious to me. The best thing to do, which is what I will do in the following, is to say that death rate and the division rate depend on pressure. So if you increase pressure, cells divide less and cells die more. The thing that comes in here is what I will call the growth rate or the proliferation rate, which is the difference between cell division and cell death. If the pressure is very low, cells are very happy, they can divide. If you increase the pressure, you compress them, they die more, they divide less, and this quantity decreases until a point where cell division exactly compensates cell death, up to fluctuation, because cell death and cell division are stochastic processes. But on average, you create as many cells as cells die. This is what I will call the homeostatic pressure of the tissue. This is the pressure of the tissue in a steady state. Now, for a long time, one of the things we wanted to do is have measures of the homeostatic pressure. There are many ways to do it. I'll tell you an experiment that was done at Institut Curie a long time ago by this person called Fabien Montel. So what he was doing, he was taking spheroids and he was exerting pressure on the surface of spheroids. And the way you do that is you use osmotic effects. So you put something outside that doesn't go inside the spheroid, that increases the osmotic pressure, and the pressure difference is equal to the osmotic pressure difference. The types of pressures that we apply is something like 1 kilopascal on the surface of the tissue between 1 and 10. So how do you do the experiment? You start with a few cells, a small aggregate, and then cells divide, and the spheroid grows, and at some point it reaches a steady state. At steady state, the size is about slightly less than a millimeter, half a millimeter or so. So we There's another experiment that you need to know of, which is this one. What they did here is that they looked at cells which are dividing and cells which are dying. So there are ways in biology to do that. The red cells here, which are inside, are dying, and the blue cells, which are on the outside, divide. So it means that in these spheroids, cells grow on the outside, they move inside, and then they die. And the way I didn't show you growth rates, but you plot the volume as a function of time. And the way we fit it is the most naive theory that you can make. We assume that it's roughly incompressible. So the volume and the number of cells is the same thing. This is a bulk term. This is what I wrote before. Cell division minus cell rate times the number of cells or the volume. And then cells divide more on the surface. So I add this surface term here. V to the 2/3 is the number of cells on the surface. And there's a length, which is the length, this length here, where cells divide. And the way we treat this length is we just fit it to the experiment. So in this case, it was 50 or 70 micrometers. It fits perfectly well. And we only have two parameters. This is the growth rate on the surface. And this is what happens in the bulk of the tissue. So if I look for the homeostatic pressure, it's when this goes to 0. So the growth rate on the surface doesn't depend on the pressure that we apply, for instance, in these two cases. And the growth rate in the bulk goes in the direction that I mentioned. It decreases when you increase pressure. However, if I reach 0 pressure, it's still negative, which means if I want to go to the homeostatic state, I will have to extrapolate that and see where it reaches 0, which means that the homeostatic pressure is negative. So this is the reverse of what you find in Landau-Lifshitz at page 1, except that this is a non-equilibrium system. So what Landau-Lifshitz tell you about thermodynamic is not true. You can have negative pressure in tissues. You can have negative pressures because cells divide and cells die. So much, biologists have known that for a long time. They call it tension. So what they call tension is minus the pressure. So if I extrapolated, I would find some negative homeostatic pressure. Why is the homeostatic pressure negative? Why is there this surface effect here first? There are two reasons. One is obvious. The obvious one is nutrients, because nutrients are in the liquid around and they diffuse inside. So the cells on the outside have a lot of nutrients and they divide well. And then they eat the nutrients. So the further you go inside, the less nutrient you have. And the cells inside have no nutrient and they die. There is a less obvious reason. And the less obvious reason is that when a cell divides, it has to push its neighbors. And it's easier to push the neighbors when you're on the surface because you have less neighbors. It's exactly the same kind of ideas that people like Young and Laplace in the 18th century were putting forward to define the surface tension. Here, the fact that you have less neighbors makes it that the force or the mechanical forces that you have to exert are smaller. So it's easier to divide on the surface. And this is part of the effects that you see here. What I want to show you is a numerical simulation that was made by a former postdoc of ours, Jens Elgetti. It doesn't use this spherical geometry. It does it for vertical columns of cells that he reproduces periodically. Cells divide on the top and they die inside. So you will see this layer of cell grow. At some point, the height becomes large enough that the death inside the volume compensates the division on the surface, and you reach a steady state. So that's what you should look at first. So it grows, watch on the right-hand side. So here it grows, and it will stop about this level. On this side, what he has put is a solid surface. But on the solid surface, cells still have to push to divide. So my surface effect due to mechanics just disappears. And you see what happens? The cells contract. So we put a spring, and the force exerted on the spring that pulls downwards is just a negative pressure that pushes the tissue downwards. And if you reach a steady state, you reach a homeostatic state in this precise configuration. So we wanted to know more about that. And I won't go into the details with a postdoc, Doron Grossman, recently. we studied two-dimensional tissues, like the one I showed you before, using what people call a vertex model. The idea is that you take this tissue, so this is the tissue that biologists love. It's the wing of Drosophila, or what will become the wing of Drosophila, which is a fruit fly. And you see that they watch it from the top, and they label the interface between cells, the membrane. And you have some kind of graph here. So what people decided is that knowing that is enough to decide what happens to the cell. So you pinpoint all the vertices, you decide that these lines are straight, and you describe your tissue by an area of polygon that paves the plane. Now, of course, you need a physical law to see how this evolves. The way this is classically done is to say the cells have a preferred area, and they have a preferred perimeter. So the preferred perimeter is due to the surface tension, and the area is something which is slightly more subtle. If you look more into that, if the cells are pretty flat, this is a very good approximation. So considering that they are two-dimensional is a very good approximation. If the cells are very elongated, which is what's drawn here, the approximation is less easy to justify. So what we did is we took this model, we put the cells in a box, which means we put walls on both sides. We let it grow, and we calculated the pressure when it grows. So this is what's plotted here. This is the pressure, and this is the growth rate of the cells, but it's a growth rate of the cells but they are fully relaxed. If I would take an individual cell, it's active because it eats nutrient, and what its activity does is that it makes it divide. So this homeostatic, this growth rate increases if the cell is more active, and at large division rate, the osmotic pressure is positive because you make many cells and they push on both. If you take small values of the division rate, it depends on the properties of your cells. And there are essentially two types of cells that you have in this model. One is when the cells are fully relaxed, which means they're not pre-stressed, and when they are fully stretched. If they are not pre-stretched, the homeostatic state when there is no division is exactly 0. But if the cells are under pre-stress, which is a case where they have a finite shear modulus, if this is large enough, you find a negative homeostatic pressure here. So the way you can reach this state with negative pressure is you want that there is no pre-stress on the cells, and also you want that this spontaneous division rate is not too high. So that's where we are with this. Now you can worry on why is a tissue a liquid. I already told you that the cell has to push on its neighbor, which means that the mechanic influences cell division and cell death, but the reverse is also true. And there is this old experiment that was done at Institut Curie by a PhD student of Mathieu Piel. What he was doing is he was taking a sheet of plastic, which was elastic, of rubber, and he was letting cells divide on the rubber, and then he was pulling on the rubber. And the cells divide, so you have to watch this movie. What you see on the right is a metaphasic plate, which is the cell divides in a perpendicular direction, and this is always perpendicular to the direction where you pull. And then they did all kinds of crazy things. The cells started dividing in one direction, they pulled in the perpendicular direction, and the whole thing rotates, and things like this. But the output of that is that if you put the cell under stress, it aligns with the eigenvalues, the eigendirections of the stress. So the way I will use that quantitatively is I will look at the orientation tensor. I cannot put a vector because plus and minus directions are equivalent. It's like nematic liquid crystal. So I have to define an orientational tensor. The tissue can be oriented, but then the orientation is modified by the stress, and I just use a linear approximation. So if I pull more, I orient more in the direction of the stress. That's one effect. So this, if you define the orientation here, this is how I define the orientation tensor, which is a nematic order parameter. The other thing I want to put in the theory is that when cell divide, it exerts, so it cannot exert a force because there is no inertia in these systems. So the total of the forces on the cell should be 0. So the only thing that it can exert is either some isotropic pressure, so you push isotropically, and if you want to do it in one direction, you have to exert a force dipole. So what will be important here is the force dipole that the cell exerts when it divides. The other thing you need to know, which I didn't know, but if you put a force dipoles like this in a fluid, the density of force dipole is exactly a stress. So there is a stress due to cell division and cell death in the tissue. Now, I sketch here the argument of why the tissue is liquid. The total stress is the elastic stress of the cells. Each cell has an elastic modulus, plus this internal stress, which is due to cell division and cell death. And if I take into account these two effects here, what I get in the end is a relationship between the stress and the velocity gradient, which I wrote here. So if you forget this term, and if you know about polymers, like Alexei does, this is exactly the equation for a Maxwell viscoelastic fluid. It's solid at short times, which means if you deform, it reacts as a solid. But then if you wait, it flows, the stress relaxes, and the solid which has relaxed its stress is a liquid. So there's a time scale here, and the only time scale in the problem is the cell division time. I didn't give any numbers. This is 1 day. So if you work for 1 day for cancer cells in the spheroids that I showed, if you want for 1 day, it wants to flow. And then there's a finite viscosity. And the viscosity is the elastic modulus of the cells times 1 over the division rate, which is the cell division time. And if you put 1 day and 1,000 Pascal, which is the elastic modulus of the cells, you get the numbers that I gave, that the viscosity of a tissue is like 10 to the 8 times or 10 to the 9 times the viscosity of water. The shear modulus of a cell is extremely low. You know what I mean? Like, this is 10 to the 11. Rubbers are 10 to the 6. 10 to the 3 is like these jellies that the English people like to eat at breakfast, stuff that shakes like this. This is about the consistency, the elasticity of a cell. So if I forget about this term, this is a viscoelastic fluid, and you can calculate the relaxation time. But there is another term here, which is proportional to the orientation of the tissue times the prefactor. So there's no way you can derive that from any theory of oriented fluids if they are at equilibrium. So that's a non-equilibrium term. This is why I put something that I call delta mu here. The energy in the cell comes from ATP hydrolysis, and what you gain is a free energy, which is 25 kT per event of hydrolyzing ATP. So there is a stress which is proportional to the local orientation tensor, and which is a non-equilibrium effect. The only thing I want to say at this point, and then I will give you details, is that the nematic tensor is not isotropic. It has 2 directions, and the trace is 0. So there is one direction like this, and in the other orientation, it compresses in the other direction. So this active stress has an eigenvalue along the principal direction that can be extensile, so it can pull on the tissue, or that can be contractile. The tissue can contract due to its activity. And both cases exist for tissues. If you look at experiments, typical orders of magnitude are again something like 1,000 Pascal. These terms mean that the tissue is active. Now, what I call something active, it's a liquid where each component consumes energy. The tissue consumes nutrients, so I could have guessed that there would be a term like this. And this is what I want to describe now. Before I do that, we also looked at very strong deformations of tissues. So the same 2-dimensional tissues that I showed you. The way the calculation is made is we impose a shear rate, and we look at the function of time, how the stress varies. So the shear stress varies. What we plot here is a constant shear rate that we apply times time. So it's a deformation. So at very short time, the stress is proportional to the deformation, which means the tissue is a solid. So I could measure what I call the elastic modulus G here. Then there's a maximum, and then the stress goes down. And at very long time, or very large deformation, you reach a steady state, a new homeostatic state under a constant shear rate. If the shear rate is very low, this stress is proportional to the shear rate, and the ratio is just a viscosity by definition. So there you see the viscosity. And if you go to high shear rates, the tissue becomes shear thinning, which means the larger the shear rate, the lower the viscosity. Paints are like this, for instance. If you apply a force on your paint, it goes easy. And if you don't do anything, the viscosity is very high. Now there's this maximum here. There are fluids like this. Again, polymers are a good example. If you take entangled polymers, the shape has this form. And fluids like this, where the viscosity depends on time, and there is a transition between liquid and solid, are called thixotropic fluids. So these tissues, at least the two-dimensional ones, and they have zero theory in 3 dimensions, are thixotropic fluids, which are thinning at very high shear rate. So that's what happens if you impose a very strong external force. What I want to describe now is what happens due to the fact that the tissue is active. I'll show you first experiment, and then I'll try to explain them. There are 2 experiments here that were done in the group of Pascal Silberzan, a former student of Liliane, at Institut Curie. And the experiment is extremely simple. This is a solid surface where they put cells on top, except they made a band. And on this band, the cells have to stay on this band. They are stuck on this band and they cannot go outside. So the band is here. And what you see here is a slice which is cut in the middle. At the edge, the cells are parallel to the edge. That's an experimental fact. But if you look in the middle, despite the fact that you don't do anything, there are a transverse angle, which is something like pi/4 in this direction. Now, if I wash this stuff, and I wash for a long time, the tissues flow spontaneously, and it flows spontaneously without any pressure gradient. So there is flow without pushing on the fluid. So that's what I want to show you. It goes up in this direction. It goes down in this direction. The most spectacular thing in that is the values of the velocity. It's micrometers or fraction of micrometers per hour. So to move by 1 cell size, you need to wait for 10 hours or something like this. And if you look at the number, I can rerun it. If you look at the numbers on top, the experiment lasts for 3 days. So you have to be very patient to see that. But there's a well-defined flow, which is almost a constant shear in the middle of this tissue. There's even more to it. Which is what's shown in this picture here. It's the same type of cells. These cells are elongated. This is the only property that they have, and which is strange. The only thing that they did is they watch it over a much larger size than on the left-hand side. So here it was something like a few hundred microns. Here it's millimeters. And you can, so this is what happens if you look at the cell from the top. And this is a velocity field. First thing is that there is a velocity field. So here again, the cells are moving spontaneously. The orders of magnitude are the same. And what's plotted here is the vorticity. So the curl of the velocity tells you how locally the tissue rotates on itself. You see that there is an array of vortices that covers almost all the tissue, and you have vortices of all signs. So some vortex turn in the right direction, some vortex turn in the left direction. And then there are ways to quantify the vortices and the area. The area of the vortices decays exponentially with the size. So there is a distribution of vortices. The only thing that I know where there is a distribution of vortices of both signs is turbulence. So what people did is they call that active turbulence. And the fact that, so the activity is kind of this active stress. I will show you in a minute that the fact that you increase the size of the system increases the activity. So at very high activity, or I could reach the same, what it means is I could reach the same state by increasing the active stress in this situation. What it tells you is that if you go high in activity, the tissue becomes turbulent in the sense that there is vorticity. However, the Reynolds number is exactly 0. It's smaller than 10 to the minus 6 in this system. So this has nothing to do with hydrodynamic turbulence. People call it active turbulence. I'll try to tell you a little bit more about these 2 situations now. Before that, I will give you a very, very small introduction to active fluids. which has become a huge area of research, which should be very easy in Orsay because it's almost the same as the hydrodynamics of liquid crystals that was invented here. But in the 70s, I wasn't doing science at this time. I was too young, and I guess most people in the room weren't. I will give you names of some who are doing it. So the simplest model that I know is I take a one-component fluid. The fluid is nematic, and I will assume that it's deep in the nematic phase. So the only thing I have is a director, and the director is a vector of modulus 1. And it's active, which means each of the components consumes energy. Each cell consumes energy. And then what we did is we applied exactly the same procedure that people apply for liquid crystals, which means you write Onsager relations, and then you use symmetries. And the equations that we get are here. They're a little bit messy, but if you forget this term, which is exactly what I told you was an active stress, all the rest is what people in Orsay used to call nemato-hydrodynamic, which is the hydrodynamics of liquid crystals. There is a viscosity. In fact, there are 3 independent viscosity. I just assumed that they were equal to make it simple. There is a coupling between the orientation of the director and the stress, or the velocity gradient. This is called the flow alignment term. If you shear, you orient the molecules. And then there is an equation for the orientation. There is an external field. So the external field is such that the cells want to align. And so if they go at an angle like this, or a gradient of angle, because if everyone is parallel because of rotational invariance, nothing happens. That forces the cells to become parallel. It's well known that in 2 dimensions, this external field is some constant, which is a Frank constant. Again, there are 3 of them, and I assume that they're all equal. And that relaxes the tissue to a constant alignment. So I have, this is what's called the rotational viscosity. It tells you how fast it aligns. This is the translational viscosity, and I have this flow alignment parameter, which is here. The only thing which is not like in liquid crystal is that there is this active stress, which is here. I told you that it can be extensile or contractile. It can extend the fluid or contract the fluid in the main direction. If this flow alignment parameter nu is positive, the elements are disks. If it's negative with the convention I chose, they are rods. So the cells that I showed you were rods. So in the following, I use nu negative. In all the experiments I know, whether they are on liquid crystals or anything, nu is extremely close to -1. 1.1, I mean, there are theories for rods, for instance, where in the limit of infinite rods, it becomes exactly equal to 1. So the only thing I want to show you is what happens when there is an active stress here, and when this stress becomes large. There's a third equation. This third equation tells you how energy is consumed. There's a spontaneous consumption of energy, and this is the energy injected by the active stress in the system. So if you want to make an energy balance, you inject energy via the active stress, and this is dissipated by the 2 viscosities. So that's the hydrodynamics of active nematics. So why is there this flow instability? So if you are a pure theorist, you say, okay, I consider a very homogeneous system, no flow, everything homogeneous, constant, and you find the system is always unstable, whatever the wave vector. So you put a periodic perturbation, and the system is always unstable at linear order. How do you see that? So I made it simple just to avoid to write complicated equations. So I set nu equals 0. This is the active stress, and this is a growth rate, and it's always positive at q equals 0. This is q squared over q squared if you choose the right direction. So there is always a direction where the system is unstable at q equals 0. This stabilizes. So what stabilizes, these are the viscosities, and this is the Frank constant. So this term is positive, which means if you go to high enough Qs, very local perturbations are stable. But as long as you go to large perturbation, it becomes unstable. There's another property of this relation, is that there is no preferred wavelength, which means there is no peak in the growth rate. What it means is that the wavelengths that I will show you in a minute is not selected by the linear stability, it's selected by nonlinear effects, which is much harder to understand. Another way to look at it is almost exactly what I showed you for the cells. Suppose you have a very thin film. And what I've been telling you for a minute or two is that there's a stress proportional to the nematic order parameter. What it means is that if the orientation is not constant, there's a gradient of the nematic order parameter, and there's a gradient of stress. Now, in a fluid, a gradient of stress is a force. So if there's a gradient of orientation, the system flows. Whatever you do, it has to flow. And I showed you that on the edges, it was parallel. In the middle, it was perpendicular. As long as you see that, it has to flow if there is an active stress. Now, what happens here is that if you start from everything parallel, if you make a small tilt in the orientation, that creates a force. The system starts to flow, and there is a feedback, which is due to both rotations, local rotation of the fluid and the flow alignment term, and there is an instability coming out of that. So the instability has a threshold, meaning that if the film is too thin, the viscosities, the viscous stress are extremely high and nothing flows, but you reach a critical state and the critical velocity is given by this. L squared is proportional to the Franck constant divided by the active stress. So if I make the active stress very large, the system becomes unstable almost all the time. In this problem, you can check on my equation. There's only one length scale in the problem, which is this one. So if I want to make a dimensionless number, the only thing I can do is make a dimensionless number, which is the size of the system divided by this critical length. As I want it to be proportional to the active stress, I take the square of that, and that becomes proportional to the active stress. And that's what I call the activity. So I can make the system very active two ways. One is hard experimentally. You change the activity of the cells, or I take a large system. A large system is always unstable, as shown by that, and spontaneously flows. And that's how you reach this active turbulent state. So the first thing I want to say about active turbulence, it's not a property only of tissues. Almost any active system becomes unstable to flow and shows this active turbulent state. There are all kinds of experiments here, bacterial suspensions. And in fact, the first ideas on active turbulence were made by Ray Goldstein, who is a professor in Cambridge, on bacterial suspensions. You have sperm cells in 2 dimensions. You have artificial particles, which are Janus particles with 2 sides which are different. Bacterial suspension in 3 dimensions. These are the tissues, and there are experiment mimicking biological systems using microtubules and molecular motors. All these systems show active turbulence. On the left, you have a picture of the system. This is a vorticity map that looks pretty much like the one on tissues that I showed you. And on the right, you have the velocity power spectrum, which means the square of the velocity at a given wave vector, which is what people like to measure in turbulence. However, there's no kinetic energy in my system. So I don't multiply it by the mass density because the kinetic energy vanishes. The Reynolds number is 0. And that's not so universal. Sometimes it's monotonic, sometimes it's non-monotonic, sometimes it even oscillates and things like this. So there are several types of active systems. The one I will show you is kind of the simplest one. It's described by the hydrodynamics that I showed you before. But for all of these systems, we should be able to explain the various types of active turbulence. Many of them are not understood yet. Yes?
I mean, there is, I guess if you have turbulence, you generate pattern of different scale.
Yes.
So
okay, so that's exactly what I want to do. Then you can worry, how do you characterize a turbulent state? If you talk, I mean, one of the persons, his name is on the next slide, is an expert on turbulence. For him, it's 2 things, and we stuck to that. One is the fact that there is energy transfer between scales, and I will show you in a minute that this is very small. And the other one is that you find scaling laws. And for hydrodynamic turbulence, you have this famous Kolmogorov scaling law, which is exactly this velocity power spectrum, which in 3 dimensions decays like k to the minus 5/3. And you know that in 3 dimensions is due to vortex stretching and things like this. And you have vortices of all sizes. It's not the case here, because I told you that the distribution of the size of the vortices is exponential. So then there can be a debate on whether this is turbulence or spatial temporal chaos. I don't know. It's not very important for me. The only thing is that we have a system which is chaotic in time and space with somehow universal properties. So that's what I will stick to. Okay. So to go to this, I have 15 minutes left. It's okay, I won't go to the end. I'm not bothered by that. So here is the system. We only studied it in 2 dimensions, although we have scaling laws in 3 dimensions. And the first thing that we studied is the energy as a function of the wave vector. What is the energy stored at a given wave vector? I insist this is not kinetic energy. This is a frank elastic energy of the liquid crystal. And it has a strong peak at a given wave vector. And this wave vector, I told you that there is only one length scale. So it's 2 pi over the length that I showed before. So it's proportional 1 over square root of the active stress. The other thing, so energy is localized. And in fact, if you think about it, the active stress injects energy at all wave vectors at the same time. That's another difference with turbulence, where you, at least in 3 dimensions, you inject energy at the larger scale and it cascades down to the smaller scales. Here, you inject energy locally in real space and not locally in Q space as well. So this is what happens when the flow alignment parameter is 0. This is what happens for an extensile system, and this is what happens for a contractile system. Now we'll show you here a map of the free energy density. The way these maps are done is we look at the free energy density, which is gradient of the angle squared. And we chose a threshold, and the color is put when when you're above this threshold. So the region where the gradient of the angle is large are colored in red. This is what happens for a contractile system. This is what happens for an extensile system. For the extensile system, there's a very well-defined arrangement here that you can, I won't do it for you, but you can study that in terms of labyrinth. There is a red labyrinth and a white labyrinth that are entangled together and never cross. This exists. If you go to Chambord-Casson, there is one that you can visit. I did that with my grandson, and it says that at the entrance, that you have 2 paths that never cross. This is exactly what this stuff is doing. And in this case, you have a lot. This one is more messy. And this one, so for a contractile system, a region where everything is black. So everything is black means there are regions with constant angle, which are mixed with regions which are disordered, like in the other case. There is a distinction between the 2 cases that I didn't talk about. The distinction is, in the case where the system is extensile, the system is always linearly unstable. In the case where it's contractile, the bifurcation can be subcritical, which means it can be discontinuous. That suggests that you can have 2 states coexisting, which would be a state of constant orientation and a state where you have this turbulent or whatever effect here. And that if you go to high values, you could expect to have some kind of intermittency between the 2 states that flip between one another. So what I want to show you now, which is a picture below, is what happens if you look at the flow. So here is the ordered case. It's not static. You have long range fluctuations of the velocity. No, that's the free energy density. That's not what I wanted to show you. Sorry. Excuse me. I wanted to skip that. I have to wait a bit. So in this case, there are very small fluctuations of velocity. They are long-range correlated. In this case, you have this flip between ordered and disordered region, which is what I kind of call intermittency before. It's obvious that there are more fluctuations here than here. So this one should have larger fluctuation. This one should have smaller fluctuations. Now, what I plotted here is the velocity power spectrum. So the square of the velocity at a given wave number in 2 dimensions multiplied by q as a function of wave vector. If you go to very low wave vector, it's a straight line, it's log, and the slope is -1. So this velocity power spectrum goes like q to the -1, whatever the value of this flow alignment parameter. There is a peak in this case. So when it's extensile, there's a peak here, and you see that the system has a period. You see it with your eyes. There's no peak when it's contractile, and it's pretty disordered. This is what you see here. So there is scaling at low wave vector, which goes like q to the -1. And q to the -1 means that the vorticity is essentially local and it has no correlations if you go back to the original equations. So it's long range. It's like the solution of a Laplacian equation. But for every system, there is this law in q to the -1. Then we can test energy transfer between scales. In this region here, there is no energy transfer between scales at all. So that's different from classical turbulence. Except in this region here, I told you there's a peak, but there is a second peak here. And if you look at energy transfer between scales, the system transfers energy from this peak to this one. So there is a small energy transfer between peak, not at large distances, where you see these large range fluctuations that I show that appear here, but just between these two peaks, where this is about twice the value of the wave vector at the peak. So in a sense, it's like turbulence. There is scaling, but there is no energy transfer or very small energy transfer between scales. And I guess I could stop here. I won't show you my other story. I can just show you that to tell you what the problem is. If you take cancer cells, they are usually in a primary tumor. And if things go bad, they move to other organs to make a secondary tumor. And doing that, they have to cross tissue, which is essentially an extracellular matrix, which is an elastic tissue. So the question is, how do cells move in this elastic tissue? And what people find is that there are 3 ways of moving. One way is individual cell motion. One way, like this, is cluster motion. And the other ways that we were also interested in is what you see here. There's flow of cells which are correlated with one another. So the whole bunch of cells is flowing in the whole direction. And the question that we raise is, how can we explain these 3 types of motion? I don't have time to talk about it, so I will stop here and thank you for your attention.
We have time for questions.
I didn't understand well where this period in your turbulence comes from. You have a kind of labyrinthine structure with some kind of period.
Another way to explain it to you would be, suppose I take this lane that I showed before, and suppose I take a thin film and I increase the thickness. So I showed you that at some point it spontaneously flows. But then if I increase it twice, instead of having a profile, which is when you go close to a transition is like a sine function, you make 2 arches of the sine function. Except that in practice, there's an instability in the transverse direction and things like this. But always you break the system into 2, and this is kind of where the period is coming from. You break it into 2 in such a way that when you make the system larger, the typical length scale remains the same. This is where this period is coming.
Larger,
in both directions in practice. I mean, the thin film is very anisotropic, so it's an easy way to explain it. But if you take a square system, the system becomes unstable. In the beginning, it makes two bands, and the direction of the two bands is chosen by the orientation that you start from.
But your system also has some thickness.
Oh, it's in 2 dimensions.
It's only 2 dimensions.
I mean, the instability exists in 3 dimensions, but everything which I showed is in 2 dimensions. So it exists in 3 dimensions as well. But you break the pattern every time to keep the same period that you had in the beginning. Now, what's the precise mechanism to do that? I don't know. I mean, I can show you what we think, but I don't have the movie. So this is the orientation.
Yeah.
There are strong gradients when it's red, and it's oriented in the same direction when it's black.
So what is the color code?
So the color code is the gradient squared of theta, where theta is the angle. So it means there are walls between regions which are essentially of constant orientation. It seems that the way this stuff appears is by branching of the walls. So the wall which is straight will branch in the perpendicular direction and make another wall at this place. That's what the simulation suggests, but I have zero theory to show you. I can show you movies, I mean, if you want, but I have zero theory to explain that.
Is there some kind of similarity between these kind of patterns and the electroconvective instabilities of liquid crystals in an electric field?
This question I don't know, I can't answer. There's another area of science, even of soft matter, which is called elastic turbulence. If you take a very entangled polymer and you put it in a quet system, you rotate the quet system in such a way that you don't create, I mean, I think you have to rotate the outside and not the inside. Still, the system becomes turbulent, which is a story of normal stress difference and things like this. And it has this stuff has some features of turbulence. So it's purely of elastic origin. And I think it has transfer of energy between scales. People prove that. That's the only other case where that I know where there is well-defined turbulence at low Reynolds number. And for the electroconvective instabilities of liquid crystals, I'm sorry. I don't know about. I mean, I know they exist, but I don't know more than that.
Thanks for this presentation. I had a question about the homeostatic pressure that you presented at the beginning.
Yes.
And I mean, the model you presented is something where the growing is isotropic. How does anisotropy plays a role in this homeostatic pressure? Does that play a role or not at all? Or
so what I told you is that the growth rate or the division rate or the death rate depend on pressure. If your system has some orientation and things like this, you could say it doesn't only depend on pressure, it depends on any scalar you can make with the anisotropy of the system and the stress tensor. So there are two questions. One is, are there homeostatic states? And in most of the cases I know the answer is yes. The other one is the pressure sufficient to characterize them? And I would say the answer is no. It could depend on the shear stress, for instance, if you could make a scalar with that, which is not the case if your system is isotropic.
So, two questions. One question is about the 2D layers. So, do you have extracellular matrix between the cells? Or?
In 2 dimensions.
Yeah.
I would say no. I know what happens in the spheroids. There is, in the beginning, there is not, but when cells die, so the thing that I didn't want to go to the details is cell divides on the outside, but suppose you reach a steady state, cells still divide on the outside, and they are carried inside by the flow. So the flow is radial towards the inside. So when cells die, the dead cells are carried in the middle. And there is a region in the middle where there is only dead cells and where there's a lot of extracellular matrix. But that's only a problem in the in vitro experiments, because in vivo, there are cells of the immune system that wash out dead cells. Of course, we don't put them in the experiments in vitro. And in practice, the way they solve that is they do the experiments for a few days, and they don't try to reach the steady state. They stopped after 3 or 4 days because the system is changing, because the cells are producing a lot of extracellular matrix. So in 3D, it exists. In 2D, I wouldn't be able to say.
So in the experiments of Silberson, so on the 2D layers, so there is no friction between the surface and the layer?
Yes, there is. So what he's saying is, I treat it as a viscous fluid in 2 dimensions, but there is also friction on the substrate. Now, there is a length scale that you can make with the friction and the viscosity. The square root of the viscosity over the friction is the length scale. And if you are at length scale smaller than that, the system is dominated by viscosity. And what I showed you here is what happens. If you are at dimensions larger than that, friction dominates and the flow is killed. So if you increase the friction, at some point, this friction length becomes smaller than the size of the system, and the instability disappears. We studied that. There's another weird effect, which comes in the beginning just from the experiment. So they measured velocity, and they measured this shear velocity, because that's what you see with your eye, but there's also a transverse velocity. And the transverse velocity, the only explanation we have that seems to be true is that some cells are expelled in the middle from the system, and that as the system wants to remain at constant density, that creates a transverse flow towards the inside. So there are other things, this kind of stuff we studied in details. And the friction can be treated exactly the way I showed, but in a sense, if you make it too large, it kills the flow. Same thing for the turbulence. The intensity of the turbulence decays very strongly with friction, and the power law exponent that I said changes when you put too much friction.
So the cells are, you have multiplications of cells, and some cells are dying.
Yes.
Apoptosis.
Apoptosis.
Okay. But what happens with this cell that died? Do they conserve the volume or not?
So
what about the volume?
As I said, in 3 dimensions, that's no problem, because there are cells of the immune system, which are called macrophages. They patrol around. And so what happens when apoptosis is very clean. There are small debris of cells, which are vesicles and stuff, and this is all eaten by macrophages. What happens in the spheroids, they are assembling at the core, and they make what people call a necrotic core, where things are extremely different than what happens outside. Even the pH is very different. And there's another effect, which we never took into account, but many people mentioned it, which is that cell death is contagious, which means if you make a core of dead cells, the neighboring cells have a tendency to die more. So that's well known by biologists. So it means it's more complicated than when I say. In practice, in the experiments, they don't see it because they stop the experiment before the core is too big. And in this case, the number of dead cells is small. And in vivo, there is no problem. Everything is eaten. I mean, I don't know. I don't know if it's no problem, but at least everything is eaten.
I had a question about the energy cascade. So in the classical turbulence, you sort of control at which length scale you input energy. Here it will seem that there's energy on all length scale, which can fluctuate with the nutriments. So how?
So here, energy is injected at the scale of the nutrients. So at the smallest length scale you have in your problem, you inject the energy. Mm-hmm. Now, the energy is stored. And when I showed you this curve here, I don't know what I did, but anyway, this upper curve here tells you that energy is stored at a wave vector, which is the wave vector of the peak, more or less. So when the system flows, it redistributes its injected energy to make it stored at the scale of the peak. Mm-hmm. Then either it's dissipated locally by viscous friction, and there are 2 frictions. There is a rotational one and the translational one, or it's transferred to other length scales. At nu equals 0, which means if there is no shear alignment, we can show that with the equations that we gave you, there is no energy transfer at all. There's a symmetry argument that shows that. In this case, we didn't see it in the beginning, but there's a small peak here. And if you calculate the flux of energy, there's a flux of energy from here to here. So there is a little bit of an energy transfer, but it's not self-similar as it is in regular turbulence. So the way you have to do it, you have to do it in wave vector space. You look at the energy in a given slice, and you look how it evolves with time. There's injection, there's dissipation, and then there's the flux of energy. If in this case, where there is no shear alignment, the flux is exactly zero. In the other case, it's not, and there is a small transfer between this.
The second peak, half period of the previous, the big peak.
I don't know the precise number. It's a finite number, two times.
About two.
It's about two, yes. Yeah. I don't know how to, I mean, we show it here. We check that there is a flux just by looking at the curve. It tells you that there is, but we are not able to do that more precisely. It has to be a number. I told you that there's only one length scale, or two, the size of the system and the period.
Two some.
So as obviously it's not the size of the system because I can go to very low wave vectors. It has to be something proportional to the period. It's a bit hand waving, but somehow it couldn't be wrong.
So if there are no more questions, we can thank Jean-François once more.